of models for the transient development study for electrical systems, long distance transmission, computing applications for the simulation of transients in electrical systems. Thank you, Camilo. I'm going to present a study that was part of the half wavelength when the transient studies. The title is TRV requirements imposed to the Serra da Mesa circuit breaker during the opening maneuver at the AC test link. The motivation behind the study is that the circuit breaker at Serra da Mesa, in the link being part of the study, was dimensioned for different conditions than the ones proposed in the test. So different operation interruption condition than those proposed on the AC test link. So the goal of our work was to get the requirements, the TRV requirements, and the circuit breaking terminals in Serra da Mesa during the energization maneuver, with a specific purpose to check the service or surpassing for different operation conditions for the circuit breaker with the opening of the link in a non-load state with no fault and under several different fault conditions. This is the link proposed to the test. This was already presented in several other talks. It is composed by the north-south interconnection and the north-south 1, north-south 2, and part of the northeast-southeast interconnection. Our study is going to concentrate on this circuit breaker, remembering that all the other circuit breakers in the link are interlocked to form the 2600 kilometers that 460 hertz would correspond to a little bit more than half a wavelength. The TRV event has a short duration, usually the first 2 milliseconds after the switch is opened. So this involves high frequencies, and automatically you need to have more details of the models for the components, especially for the circuit breaker. Here you have some specific conditions for the study that were used for the test. It was done with a single generator due to an operational problem in Serra da Mesa, so the generator has 492 MVA. The pre-maneuver voltage was 1.1 pu, which would be the maximum operating voltage for the circuit breaker. On the side of the Serra da Mesa transformers, we could get the parasite capacitance and also the parasite capacitance on the circuit breaker at 8F. Simplifications, these TRV values we are going to show in the result, they were obtained in an approximated way without the modeling of the electrical arc, because we know that the TRV peaks that were obtained with the presence of the arc tend to be smaller. So the values we are going to present can be considered conservative. The circuit breaker in Serra da Mesa is a 500 kV one with a possibility of interruption of 40 kiloamperes, and with a project that is attached to the standard NBR 7118. Here presenting just some data for the modeling of the transformer in Serra da Mesa. It was a Y delta transformer. That's how it was modeled. We considered losses on the enrollments and the magnetization curve with data presented in this table and this graph. Here you can see the tower silhouettes throughout the link. We talked about this in other presentations. These lines, they have similar characteristics. In the table you can see that the positive sequence data are very close to each other, and it was demonstrated in a previous study that this line can represent a half-wavelength line without further problems regarding the transients. In our simulations, we considered the longitudinal parameter models that are depending on the frequency modeled on PSCAD. Due to an operational problem, the surge arresters were capped throughout the link, and the characteristic curves and operation limits are presented in this table. So the limits that we are using is 5 megajoules. During the study, we also did a study without the surge arresters just to verify the data. The simulated cases on PSCAD were the opening of the AC test link with no fault, which is the proposal for the study, and the other fault conditions. The opening of the link with terminal faults, so in front of ahead of the circuit breaker. So single phase ground, 3-phase ground, and 3-phase isolated. So opening of the link with kilometric faults. For kilometric faults in the first 5 kilometers ahead of the circuit breaker, we created single faults ground with the last pole to open, which implies in larger growing rates. Opening of the link with remote faults, meaning faults that are larger than the 5 first kilometer, from 10% of the line on. We consider single-phase ground faults, 3-phase ground faults, and 3-phase isolated faults. The integration time for modeling was 1 microseconds for the terminal faults that need a shorter amount of time, and 10 microseconds for remote faults, knowing that the transit time in the link is around 8.33 milliseconds. The data that were monitored during the study was the pre-maneuver currents in the circuit breaker and the TRV parameters in the circuit breaker. So the first reference voltage, the value of TRV, and the growth rate. And we also monitored the voltage profile in all the bus bars throughout the link. Here I present the criteria used to assess the performance of the circuit breaker during the simulations. And that's when you're simulating terminal and kilometric faults. Data from the TRV that were obtained for the half-wavelength line were compared with the TRV data considering the opening of the segment between Serra da Mesa and Gurupi. With this, considering the compensation of the segment between Serra da Mesa and Gurupi. Just as a reminder, the circuit breaker was designed to open this segment in the line. What would be the purpose of creating this criterion was to get a comparing base to analyze the results. So if the circuit breaker is open and the TRV parameters are smaller than the ones the circuit breaker was designed for, we can affirm that the circuit breaker opens the line under conditions of terminal and kilometric faults. For remote faults, we analyzed and we verified if the parameters obtained during the TRV were or not within what was established by the standard for the circuit breaker. Results. Here I present the results considering the opening of the link in a non-load state and without fault. So for the regular proposal of the study, opening of the link, non-load. In this graph, I show the voltage profile before the maneuver. So the voltage of the line before the circuit breaker is opened. This voltage profile is something we were aware of. So with the decrease of voltage in the middle of the line, here I'm comparing cases with and without surge arrestor. It was expected for the surge arrestor not to work in this case. And on this other graph, I present the capacitive current that was interrupted by the circuit breaker. The standard establishes for the opening of the circuit breaker a current of 710 effective amperes, and the current obtained for the half wavelength line was way below the established current by the standard. This line behaves like a short line for opening with no faults. Here I present the overvoltages in the terminals for the circuit breakers. The norm value for overvoltage, different from the TRV in the circuit breaker, the one established is 1200 kilovolts, and the one established for the half-wave length is 477 kilovolts at the peak. And here the TRV values. So we can affirm based on these results that there will be no problems in using the circuit breaker to open the line according to what was proposed in the study. And then we conducted analysis with the opening for terminal faults. I'm going to present the results for terminal faults. In this graph you can notice that the current value is presented for single-phase ground terminal faults, and for three-phase ground terminal faults, and also for three-phase isolated terminal faults. We can notice that the values we obtain for the for half wavelength plus line are always below the ones for which the segment was designed for. Remembering that the segment is compensated. Here I present the TRV requirements. First, the reference voltage, the Christ value, and here you have the comparative graphs showing the values we obtained, showing that the half wavelength line always presents smaller values in relation to the segment between Serra da Mesa and Gurupi. For kilometric faults, the results obtained were similar. We analyzed the first 5 kilometers ahead of the circuit breakers. This is the interrupted current, This is the interrupted current considering the segment between Serra da Mesa and Gurupi, and this is the interrupted current in the line considering a terminal fault for this half-wave length line. The results obtained show that the half-wave length line has a better performance for the segment between Serra da Mesa and Gurupi. Showing the different cases, the first reference voltage, considering both cases for the half-wave length line, the voltage peak for the TRV, and this trend continues for all types of faults. For kilometric faults, just remembering that we consider a fault the last opening of the pole, the opening of the last pole. And here a summary of all the TRV requirements comparing the half-wave length line with the segment between Serra da Mesa and Gurupi. For all the parameters, the half-wave length line showed a better behavior for openings with kilometric faults. Based on these results, we concluded that for kilometric faults and terminal faults, and for the proposal of the essay, which would be an opening without faults on a non-load line, the circuit breaker deals with these events without any issues. Here I present the results for opening of the link with remote faults. What we did was a scanning of all the faults throughout the link, varying the application of the fault in 10% segments of the total length of the line, with the purpose of verifying all the critical or severe conditions regarding single-phase ground faults, three-phase ground faults, and three-phase isolated faults, and critical conditions for the opening of the circuit breaker. In this graph, we present the current profile for single-phase ground fault. What we noticed was that there's a different behavior for the half-wave length line in comparison to short lines. When the fault goes far from the generator terminal, this decreases until approximately the middle of the line, and this is a normal behavior for a short line. From this length on, due to a positive sequence resonance, we have an increase in the current, which is unusual behavior for conventional lines. This also happens to three-phase faults that I'm going to present to you. So this region makes the current grows not for terminal faults, which is the case of a TRV analysis, but for the resonance region. So there is a resonance region making the current, the fault current, rises. The worst fault condition happens in this region, and it is superior to the terminal fault. The worst case of terminal faults, you can notice, happen between 75% of the line and 95% of the line, where the fault current starts to decrease again. Even with the increasing current for single-phase faults, the circuit breaker is not surpassed. But although, as Professor Marcos showed in his presentation tomorrow, there is energy dissipation in the Bom Jesus da Lapa surge arrestor. This is the profile, this will be the profile of the first reference voltage for single-phase ground faults. Remembering that the maximum value that was obtained for the current for remote phases was 0.6 kiloamperes, which correspond to 17% of the interruption capacity of the circuit breaker, and the curve we used as reference for service or not would be the standard curve, which is immediately above this standard, which is 30% above the capacity. So for single-phase fault, the circuit breaker is not surpassed by the TRV, as the graphs have shown relate. And these are the standard values, and these were the values obtained during the simulation. This graph shows the profile for the crest value. As I mentioned before, both the first voltage, reference voltage, and the crest value and the reference growth are within the standardized values. In these two graphs, I present the current that was obtained, varying the fault from the generating terminal to the receiving terminal for three-phase ground faults and three-phase isolated faults. We notice an identical behavior to the single-phase fault, but here there's no involvement of the zero sequence component because it's a three-phase fault. So this current levels in the resonance area are larger. And for this case, I have problems to open the circuit breaker without the use of any methodology to remove this line from the resonance condition. It's important to highlight that these current levels are way above the terminal fault in this resonance region, and as I mentioned before, for three-phase faults they are more severe. What happens with this elevation in the current is here, because here I present the overvoltages in the bus bars for three-phase ground and three-phase isolated faults, which are the most severe cases. And this study was done for 500 simulations. It's a statistics study showing this blue graph. The blue line in the graph shows the average of the overvoltages in the link. This is the maximum voltage level in the link without fault, and this other is the maximum voltage level in the link. This is the average value of the voltage with no fault, maximum value of voltage with no fault, and this is what happens, the green one, when I have a three-phase fault in a critical area. Due to the increase in the current, I have an overvoltage on the bus bar forward to the fault. What we propose here is the decrease of the insulation distance close to a substation around Imperatriz. You can notice that this overvoltage only happens when I have a fault in the three-phase region. So we simulated on PSCAD this disruption to reduce this current level as being a three-phase short circuit controlled by voltage. And in this way, we can reduce the voltage line and remove pressure from the circuit breaker. This is the same graph presented before, but with the tripping off this reduction in the isolation chain. Remember that a three-phase fault in the Imperatriz region is not severe for the circuit breaker, so I can reduce the level of the current, and with that, the TRV, I can obtain smaller TRV parameters than the ones in the standard. Remember that this fault is a fault that has a very low probability of occurrence. Here I present the crest value for the TRV with the reduced isolation distance, the growth rate. So and all these values are below the standard values. The main conclusions from the work is that from the obtained results we can conclude that the circuit breaker covers the opening maneuvers of the link with no faults and non-load. For the terminal faults we analyzed, for terminal and kilometric faults were also covered by the circuit breakers with smaller solicitations than the one that happens in the line between Serra da Mesa and Gurupi, for which the circuit breaker was designed. The solicitations from single-phase faults were also covered by the circuit breaker, and as was verified in a study for energy dissipation in a surge arrestor, it would be interesting to check the absorbent capacity in the surge arrestor at Bom Jesus da Lapa for single-phase faults. In the case of opening on the remote phases, the circuit breaker always cover considering the methodology of removing the line in the resonance condition. In all simulated cases, the reduction of the isolation distance only works for critical phase for three-phase faults. It does not work for neither for single-phase faults nor to the opening of the link non-load, which was the proposal of the test. This way we can conclude that there are no damages to the circuit breaker, no reductions in its life cycle during the study proposed for this half-wavelength line. Thank you for your attention. His microphone is off. I'm sorry, his microphone is off. I cannot hear him. Could you please, someone, ask him to turn on his microphone? The booth cannot translate the question because the microphone is not turned on. As I was saying, the question refers to the kilometric faults. From what was presented, the application distances for the defect was 2, 3, 4, and 5 kilometers. The results, the crest value and the TRV, grew as the short circuit became closer to the bus bar. So it was larger for 2 kilometers and smaller for 5 kilometers. Is this an indication that we should investigate a little bit more for 1 kilometer, for example? What is the criteria that you used When choosing this application distance for the defect, and maybe here our expert from CEPEL, Dr. Roberto, can help us with this. You are an expert in transients. Because what I understand is the substation, the bus bar arrangement in the substation has physical distances. And the substation itself has its natural frequencies of oscillation. And this kilometric distance must be chosen in a way that the natural frequency for this segment you are assigning as a kilometric distance reflect frequencies with the same values in the bus bar arrangement in the substation that would characterize a more critical situation. But you're not representing the detail of the bus bar in the substation. Could you comment on that, please? The only detail we represented to improve both the issue of numeric oscillation when the opening of the circuit breaker was the consideration of the capacitance both backward and forward to the circuit breakers. We did not model this to this level of detail on the circuit breaker. João, in this stage of the work, we still not went into the details of the substation. We started in 2 kilometers, we have a terminal fault, and then we only have 2 kilometers. And what we are seeing is that it was always less severe than the existing line. So that's what we were basing ourselves on. Both simulations, both for terminal and kilometrical, were less severe. And the only important region for the fault that we call terminal, which in reality, actually the remote fault that happens throughout the line, it is only severe when the fault happens on a defined region. Otherwise, it's damped and there's no problem with the circuit breaker. But at the time of the study, we are also going to have to remodel the substation and do a more thorough analysis. In this initial analysis, we did not have any problems. What happens is, since what we did is always less severe with the representation of the line, if it was close or above, then we would have to do a more rigorous analysis at the moment. But up to this point, it was not done, because when you're going to simulate a kilometric short circuit, you do not have a reference to choose the exact point where to apply the short circuit. Is it going to be 1 kilometer, 10 kilometer, 5 kilometer, or maybe less than 1 kilometer? This is a guide for choosing this application point. I don't know if our foreign guests have some additional information about this criteria of choosing the application distance for kilometric faults. Just to complement you, Lima, you are right. The kilometric fault, for specification purposes for the circuit breaker, you do this from 1 to 5 kilometers to define the most critical one between the growth rate and the current value. But our purpose here was not exactly this one. Just to reinforce what she said, is this circuit breaker being requested in a more critical way than the current one? And this, it was demonstrated by Professor João Bosco by using sample cases for the current situation and for the half-wave line situation. Everything is okay. This is what's interesting. We have a colleague here from FUNAS, and by creating this product, the important thing is giving the message for the assets, for the devices that belong to FUNAS. In this case, this circuit breaker belongs to Serra da Mesa. The message is making sure that the request would be lower than the one that exists today. This proposed test is a direct connection between generator, transformer, circuit breaker, the other circuit breakers that are fixated in the substations that are closed, until reaching Bom Jesus da Lapa. This way, there is no need to model the substations because everything is in series, since the generator up until the terminal. So the modeling for this test, it is not necessary. We don't need to model the bus bars in the substations since you're using the devices in series. Any other questions? Just reinforcing João Lima. And also, yes, in your question, Vanderlei, this is more connected to the substation located in Serra da Mesa. This was our major concern. But the study also involved other tools, ATP, PSCAD. Did you notice a large difference? Is there any requirement regarding the modeling for PSCAD or ATP for this study specifically? The modeling from the PSCAD is more complete. It considers the frequency variation, the parameters, the transmission lines, and with that, the results it's the most complete modeling. When compared to the ATP, the results are more reliable.